Of AXI-based FIFO, the one which I've uploaded in the group also. So if you haven't watched those particular recordings, I recommend you to watch those so that you can be in sync with what I'm discussing today, right? Yeah. So let me share my screen. Hope my screen is also visible. Please confirm the visibility. Okay. So let us start with the Verilog coding part of our AXI-based FIFO. In the previous session, we have basically discussed the overview and the top level view of how the things are going to look like in the case of your block design and how you're going to connect it with your the processor and like how the things are going to be connected, why we are learning this and where we are going to use this AXI based design. This and all things we have discussed, right? Yeah. So now let us try to understand like how to design this, right? So first of all, I'm going to design a simple FIFO memory. I hope you are all aware of how to design a simple FIFO. So I'm not going to spend more time on this since it's basic requirement prerequisite you need to have for developing a simple FIFO. So I'm declared a simple FIFO with clock reset, write enable, read enable, data in, data out, full and empty. And I've declared a memory, write pointer, read pointer. And here for full and empty conditions, I'm using a counter, or else you can write it down directly like you can have full is equal to assign full, which is equal to write pointer plus one tick binary one. If it is equal to read pointer, then you are going to get full. And coming to empty, you can simply write down as assign empty is equal to write pointer, which is equal to read pointer. So you can have these two conditions for empty, right? And if you are going to apply reset, you're going to make initialize all of them. And if write enable is equal to 1 and full is equal to 0, you're going to perform write operation. And for the read operation, you're going to make your read enable is equal to 1 and empty is equal to 0. Then you're going to read the data from the FIFO. I hope the FIFO code, it's very simple code and you have idea about the FIFO. Am I right? Shall we move forward with the top level view? I hope the FIFO code is clear for everyone, right? It's a simple FIFO. Yeah. So that prerequisite is necessary for this FIFO for this workshop. Okay. Now let me open the AXI wrapper, which is containing FIFO. Okay. So this is Testbench. Yeah. So this is my FIFO model. Sorry, this is my AXI model, which is containing my FIFO. Okay. So let me elaborate it. Yeah. Here, I have declared all the AXA related signals like clock, reset, and I have the address related signals, write address related signals. Those are your AW address, okay? That is write address and valid signal, which I'm going to get it from my master, which is a valid signal, which is corresponding to address channel, write address channel, and AW ready, which is going to given to your master. Okay. So I hope the AXA related stuff is also clear for you guys. This is prerequisite. So AXA related signals we are not going to discuss in detail. So you need to once refer to the AXA protocol, and that also is present on our channel. You can refer it. Okay. And these are the signals which are corresponding to your write data channel, like W data, W strobe. Okay, this I haven't discussed it in my videos, so I will explain you like what do you mean by strobe over here. And another is valid, W valid signal, and output is W ready. Okay, so these are the signals which are related to your write data channel. And if you carefully observe, whatever the code which we are developing is a slave. That's the reason this particular signals are inputs and this is my outputs. Okay, so depending upon the model you're going to develop, whether you're going to develop a master or whether you're going to develop a slave, the directions of the signals will be changed. I hope this particular small is thing you can able to notice, right? And coming to my write response channel, I have a B valid and B ready. Okay. So B valid is output and B ready is input to my slave. Okay. And coming to my read address channel, I have read address, AR address and AR valid. These are my inputs and AR ready is my out. Since it's a slave, right? That's why we are going to give ready signal. And the read data, R response, R valid, and R ready. R ready is input and remaining all are output. That's it. Now, I have my internal signals. One is full and empty. This I am getting from the FIFO. So let me write it down here. Getting from the FIFO. So this signals, full and empty signals, I am getting it from the FIFO. Write enable and read enable. This I am giving it to FIFO, providing as input to the FIFO. Okay. So if I want to perform a write operation from the top level module, I am going it to give to my FIFO. And if I want to perform the read operation from the top level module, I am going to give it to the FIFO. When are the signals going to become one? That we are going to discuss. Okay. And whatever the FIFO, the data it is giving you, that data we are going to collect in the top module, that is FIFO underscore D out. Okay. For collecting data which we are getting from the FIFO. Okay. Yeah. So these are my signals which are related to my EXI interface, and these are the internal signals which I'm going to have. These are some of the internal signals which I have declared over here. Okay. Now, is it clear, guys? Up to here, I hope these are clear. These are very basic things which you need to know already, right? Yes. Okay. Now, after this, we are going to declare few more signals for basically some type of synchronization. I will show you. So I have something known as AW done and W done. So AW done is a signal, or it's like a flag for representing that address operation has been completed. And another signal is W done. It's also a flag for indicating your write operation has been done. So I will write it down here. Flags for indicating completion of write address and data operations. Okay. So these are like your flags which you're going to use for indicating your completion of write address or data operation. Okay. And this particular EW underscore address underscore lat, this I'm not using currently. I'm going to use it in my future. So why I'm going to use it, I will let you know in future. And next is W data lat. This is also like it is used to store the temporary data, and this is used to store the temporary address. Okay. And next is read underscore enable underscore D. This is for delay. Okay. So why I'm going to use and where I'm going to use, I will show you. Next, what I'm going to do is I'm going to instantiate my FIFO. So clock reset, write enable, read enable, D in. So D in, if you carefully observe, I'm basically uh, assigning it from my W data latents. Okay, so it's nothing but a delayed version of my W data. And next is FIFO D out. So whatever the data I'm going to get it from my FIFO, I'm storing it into this register, and full and empty. Right. So I have instantiated my FIFO. Okay. Now, so let's see the main logic over here. This is write address channel. Now, if you are going to apply the reset, then this AW done, which is a flag, which I've shown you, right? AW done, where is it? Yeah, this is a flag I've shown you, right? For indicating the completion of write address. That particular AW done will be equal to 0. AW lat, this I'm not using it. Let me comment it. This will also be equal to 0, and aw ready will be equal to 0. Ready is equal to 0. That means your slave is not ready for the transaction, right? Now what you're going to do, else if your reset has been removed, then what you're going to do is you're basically waiting for aw valid. That means a valid address has been sent by your master, and aw done is equal to 0. That means this address has not been address transaction has not been completed. That's why aw done, if it is equal to 0, then you're going to assert your aw ready is equal to 1. That means your slave is ready for the transaction. And this I'm not using it. Let me comment it. And AW done will be made to 1. That means uh, your address phase has been successfully completed. Okay, by asserting AW ready, your address phase has been successfully completed. Okay, in the case of your FIFO, you're not going to sample the address. You don't need to sample this particular address. Okay, up to this particular design, I will show you in some scenario when we are going to increase the scale of this design. We are going to use this address also. But for now, for this particular design, we don't need of this particular AW address. Okay, we are not going to use it. So that's why I've commented it. And just what we are going to do over here is we are going to assert our AW ready is equal to 1 and AW done is equal to 1 whenever we got a valid address and AW done is equal to 0. Okay, in these two cases, I'm going to make my AW ready is equal to 1 and AW done is equal to 1. Now AW done is made to 1 and W done. I will show you. Okay. So up to here is clear. Up to this particular line 244 is clear. And it also any queries in this? Just a simple operation I've done over here. Just a simple operation of asserting my AW ready I've done over here. Is it clear, guys? Anyone having any queries in this? Please let me know. Okay, that's great. So if you have any queries, you can interrupt me and I can help you out. Like if you're facing any issue, right? Now, this particular piece of code, we will come back later in a few seconds. Now, so this was my write address channel operation. Okay, so the master, if it has sent the right address, this is what it is going to happen. Now coming to write data. Okay. So write data, what is going to happen? Again, the reset condition, W done flag will be made to 0. This W data, that is a delayed version, that will be made to 0. And W ready is also equal to 0. Okay. W ready, if it is equal to 0, that means the slave is not ready for the write transaction. Okay. And if W valid is made by the, if W valid is made to 1 by the master is going to make this W valid equal to 1, right? And if your W done is equal to 0, that means transaction is not yet completed. And W done, if it is equal to 0, then what you're going to do, you're basically making W ready is equal to 1. Okay. That means your slave is ready for the transaction. Now, coming to this strobe. Now, what do you mean by strobe is this strobe is basically a 4-bit. Now, if the LSB of this strobe is equal to 1, that means first byte of lines, that is 7 down to 0, are valid. For example, what is happening over here is here, whatever the design we are designing or whatever the design we are considering over here, let me show you in the PPT. Here, whatever the design we are considering over here, that is our FIFO. FIFO, the design we are considering here is of only 8-bit. So this FIFO is having a data in bus width of only 8-bit. Okay. But the AXI is going to have a 32-bit interface. Okay. So it is going to have 32-bit interface as W data and this will be of 32-bit. Okay. From this 32-bit, you can assume this 32-bit as 4-byte line. This is 1 byte line, 2, 3, 4. Okay. So this is from 7 to 0 and this is from 15 to 7 and so on. Okay. So this is nothing but my 4-byte lines. Okay. Now, let's say if my user or if my master is going to send this 7 down to 0 byte line. Okay. Now the slave, if it needs to, it will get basically all the 32-bit data, but it need to know, right? So which particular byte line is valid. So to indicate which particular byte line is valid, we are going to use W strobe. If W strobe, if it is equal to W strobe of 0 is equal to 1 and remaining all are equal to 0, that means only the first byte line, that is this particular byte line is valid and remaining all are invalid. Let's say suppose if my master is going to make my W strobe of 1 is equal to 1 and remaining all are equal to 0, then that means the second byte line is valid and remaining all are invalid. Let's say suppose if it is going to make the third byte line equal to 1, then that means this is valid byte line and remaining all are invalid byte lines. So using this W strobe, master is going to indicate which particular byte line is a valid byte line so that my slave can sample it. That is the mechanism which we are going to use whenever there is a mismatch in this, whenever there is a mismatch in the data size. Is it clear, guys? I hope it is clear, right? Okay. Shall we move forward? Is it clear? No, no. Yeah, it can. All 4 bits can be one at a time, but your FIFO needs only 8 bits of data now. If your W strobe is all four ones, then your slave cannot sample 32 bits now. Your slave can only sample 8 bits of data. Your FIFO interface is going to have only 8 bits of data. Okay, that's why we are going to use this W strobe. That's the reason we are going to use it. Okay, yeah. Now, now what are we going to do over here? You can see in the code also. So if my W strobe, if it is equal to 0001, then the W data, this is from my master AXI interface. The 7 down to 0, I'm going to sample it. Or else I'm going to sample the 15 down to 8, 23 down to 16, 31 down to 24. Depending upon the W strobe value, I'm going to sample. Or else by default, I'm going to sample the last byte line, that is 7 down to 0. Okay. Now I've made my W ready is equal to 1 and I'm sampling it. And after that, I'm making my W done is equal to 1. W done, if it is equal to 1, that means your write transaction has been completed. Okay. So write transaction has been completed, then your W done will be equal to 1. Okay. So here in the case of your write data channel, W done is made to 1. And in the case of your write address channel, AW done is made to 1. Okay. So if you carefully observe, we have two channels over here. One is write address channel and write data channel. So in the case of my write address channel, I'm basically asserting my AW done if it is equal to 1. And in the case of my write data channel, I'm asserting my W done flag to 1. Okay. And what I'm doing here, I'm checking for my W done also. In the right address channel, I'm basically checking whether my AW done if it is equal to 1 and W done if it is equal to 1. And also one more condition I'm going to check is full, if it is equal to 0 or not. If these three conditions are met, then what I'm going to do is in the case of my right address channel, I'm going to make my AW done is equal to 0. What happens if your AW done is equal to 0? In the code, you can observe. So if your AW done, if it is equal to 0, let me show you in the right address channel. If your AW done, if it is equal to 0, and if you are going to get AW valid is equal to 1, then again you are trying to fetch another address. Okay. And you are initiating another transaction. Okay. And in the case of your write data channel also, if your W done is equal to 1 and AW done is equal to 1 and FIFO is not equal to 1, then you're making your W done is equal to 0. If your W done is equal to 0, what is going to happen? And if your W valid is equal to 1, again you're trying to fetch another transaction data. Okay, you're trying to fetch another byte of data. Okay, and here we need to carefully insert full. If we are removing this full condition, irrespective of the FIFO memory locations, if the FIFO is full also, we will try to fetch more data from our master. That's the reason we are keeping full over here. If full is equal to 0, then only we are making W done is equal to 0. If W done is made to 0, then only we are going to fetch another data from the master. So if you are not including full over here, what is going to happen? Irrespective of this full condition, we are going to fetch the data and the FIFO will be overloaded. Okay, and the previous data will be overridden. That's the reason we are including full over here. That's it. Is it clear, guys? Yes or no? The right address and the right data channel operations are they clear? Any doubts or any queries in this? Please let me know. See this code and let me know. Simple. So just using the AXI interface protocol timing knowledge and we are implementing this. That's it. Not more than that. Is it clear? Shall we move forward? That's great. Okay. Now, after this, what we are going to do, we have completed write address and write data. Now, in the write response, what you're going to do is, again, if we are going to have a reset signal, we are going to make write enable is equal to 0 and valid is equal to 0. Now, if our AW done is equal to 1 and W done is equal to 1 and full is equal to 0 and B valid is equal to 0. Okay. So AW done means we have successfully sampled in an address and W done is equal to 1. That means we have successfully sampled a write data and full is equal to 0. That means FIFO is not full and B valid is equal to 0. We are going to make my write enable is equal to 1. What happens if your write enable is equal to 1? You are basically trying to write a data into your FIFO and you're going to give your response B valid is equal to 1. Okay. And here, if your B valid is equal to 1 and B ready is equal to 1, then you're going to make your B valid is equal to 0. Again, if your B valid is equal to 0, again, the whole process is going to start again. Okay. Here, if you carefully observe, write enable is made to 1. That means you're going to write the data into the FIFO whenever these flags are being made to 1. AW done flag is made to 1 and W done flag is made to 1. Then only you're going to perform the write enable. And not only this two, you're going to wait for this full. If this full is equal to 0 and B valid is also equal to 0, then only you're going to perform the write operation. And if you're B ready, let's say suppose if the master is not receiving the response, okay, if the master is not ready to receive the response and it is going to make your B ready is equal to 0, then what happens if your B ready is equal to 0? B valid will be 1 only. So B valid is 1, then that means the transaction has not been completed. That means you are not going to make write enable 1 for the second time. You are still making the write enable 1 for only one time only. Okay. So there is a full dependency upon each and every signal if you carefully observe. Okay. So that was about my write operation. Write address, write data, and write response. Three are basically related to each other for writing the data into my FIFO. Is it clear, guys? These three operations, these three channels, are they clear? Any doubts or any queries? Please let me know. Shall we move forward? Okay. Now, next is my read operation. So in the case of my read operation, what I'm going to do, if I'm going to apply my reset, then ready signal, R valid signal, read enable signal, and this is delay version of my read enable signal, and R data signal, everything I'm making it to 0. Now, else my read enable will be equal to 0 and read enable will be equal to read underscore enable underscore D. That is one cycle delay signal. Okay. And if my AR valid is equal to 1, that means address whatever the master is making asserting, right? So via the read address channel, AR valid signal, if it is equal to 1 and FIFO is not empty. Okay. And R valid should be equal to 0. Okay. If R valid and these are all signals are made to 0, and then what you're going to do, you're going to make your AR ready equal to 1 and read enable equal to 1. Okay. And else you're going to make your AR ready is equal to 0. That's it. Now, here, if your read enable underscore D, if it is equal to 1, then our data you're going to pad the zeros to your 32-bit to your 8-bit data because your FIFO is only going to give you 8-bit of data. This particular 8-bit of data, you're going to do zero padding and you're going to make it to 32 zeros. And you're going to give it to your whatever the art data you're going to have it, you're going to give it to that. And response will be equal to 0 and valid will be made to 1. Okay. And if your valid is equal to 1 and ready is equal to 1, you are going to make your valid again to 0 so that you can start the transaction again. That's it. So this is how you're going to perform the read operation. And this is how you're going to perform the write operation and read operation. Are they clear? Any doubts or any queries in this? Just implementing my AXI interface signals. That's it. Just using their timing behavior and implementing my data write operation and read operation. That's it. Not more than that. Is it clear, guys? Yeah. And coming to my test bench, so the test bench is basically mimicking the behavior of your master. So I've declared all the signals which are related to my test bench, sorry, the master, and I've instantiated my slave over here. And I'm basically having the right task where I'm following the protocol timing behavior and the signals like making my AW valid is equal to 1, W data is equal to data. It's a task basically. Okay. Whatever the data we are going to giving as the argument that will be that we are going to give it to my W data. and W valid is equal to 1, B ready is equal to 1, and we are waiting for AW ready and W ready. If they are equal to 1, we are making our AW valid, W valid to 0, and we are waiting for the B valid from the sleeve. And if we have got it, we are going to make our B ready is equal to 0. Just by following the protocol timing and signals, I'm writing this particular task. Okay. And similarly, for read operation, I should provide AR address, AR valid, R ready, and if AR ready is equal to 1, I'm going to make my AR valid is equal to 0. And if my R valid is equal to 1, then I'm going to read the data by making R ready is equal to 0. Okay. So what I'm going to do here over here, I've made my reset is equal to 1 and all the signals equal to 0. After that, I'm going to call this task, which is known as AXI underscore write. So this particular task will be called and all the signals will be asserted. I'm basically writing three data transactions. Okay. And after that, I'm reading for three times. Let us see what we are going to have. Let me run this simulation. Let's wait for the simulation to be completed. Yeah. So this is my test bench waveform which I'm going to get. So this is my clock and reset and AW address. This is not necessary for us, and address valid. This master is going to send AW ready and W data. Master is sending three data items and W valid. That means it's a valid data. See, for every transaction we are going to send W valid, and for every transaction we are getting W ready from the slave. Okay. And B valid, we are going to get it from the slave. Here, after completing the transaction, you can see B valid is made to 1. That means the slave is sending some response. Okay, by making your B valid is equal to 1. And before that, B ready was made to 1. Then only you are getting B valid. Okay. And AR address is not necessary over here. And AR valid, you're going to make it 1 for 3 transactions. And AR ready is basically given by the master. And next R data you can see over here. You're going to get whatever the data you have sent, right? So you can see, let me add that strobe value so that you can check it out. What is the strobe over here? DUT objects. Okay, strobe is not yet connected, so it's showing Z. So that's the reason you can see, since we have included the default case in my default statement inside my strobe calculation. That's the reason it is choosing the last 8 bits of data, EF and 3, 4 and 5. Because strobe is not connected. In the test bench also I haven't shown you any particular strobe signal, right? So here that's the reason it is connecting, it is considering the default thing. Let me show you in the AXIP wrapper. Where is my strobe calculation? W strobe. Yeah, you can see. Where is it? Yeah, you can see. So we are going to we are going to only sample the 7 down to 0. If your strobe value is none of the above, then the default statement it is executing. Okay. That's the reason you're going to get the last 8 bits of data. That's it. So this is how you're going to perform the write operation and read operation from your AXI based FIFO. Okay. Yes. So is it clear? Any doubts or any queries in this? Please let me know.